So now we will solve another problem in counterflow heat exchanger. So now we have water flowing at 20 degrees Celsius at the rate of 1200 kg per hour. So it is going to be heated by oil of specific heat capacity 2100 joules per kg Kelvin, which is flowing at the rate of 520 kilograms per hour with an inlet temperature of 95 degrees Celsius. So this oil is going to flow in the opposite direction of the water. So you have to determine the total heat transfer, the outlet temperature of water and the outlet temperature of oil. So you can take the overall heat transfer coefficient U as 1000 watt per meter square Kelvin and the heat exchanger area as 1 meter square. So in the previous problem, you have been given all the temperatures, the inlet temperature and the outlet temperature of the hot fluid, and as well as the inlet and the outlet temperature of the cold fluid. So but in this problem you will note that there are two temperatures which are unknown, which is the outlet temperature of water and the outlet temperature of the oil. So in such cases where you have to find more than one temperature, you have to choose the NTU method. So the previous problem was solved by using LMTD method. So LMTD method won't work out. LMTD method won't work out in case of problems in which you need to find more than two temperatures. Okay, so please make note of this. So now let's write the given data for this problem. So the cold fluid here is, so first note the cold fluid, its temperatures are denoted as T1 and T2, and the hot fluid, its temperatures are denoted as capital T1 and T2. So now the cold fluid here is water and the hot fluid here is oil. So now let's write the given data. So water at 20 degrees Celsius, this means the inlet temperature of water is 20 degrees Celsius. So the flowing rate of water, mass flow rate of water is 1200 kg per hour, which means m dot c cold fluid water is equal to 1200 kg per hour. Okay, so this could be converted to kg per second by dividing it by 3600. All right, so this will work out to 0.33 kg per second. So the specific heat of oil, it's a standard value 4186, which I asked you to remember, joule per kg Kelvin. And now coming back to this hot fluid, it is heated by an oil of specific heat capacity and flowing at the rate of 520 kg per hour at the inlet temperature of 95 degrees Celsius. So the inlet temperature T1, capital T1 is 95 degrees Celsius. So now mass flow rate of hot water, it will be 520 kg per hour. So which when converted to kg per second will be 0.144 kg per second. So I think you know how to convert kg per hour to kg per second. You just have to divide it by 3600. So the specific heat capacity of hot fluid here in this case is given in the problem, which is 2100 for oil, joule per kg Kelvin. So now this is the given data we have. You have been asked to take U as the overall heat transfer coefficient as 1000 watt per meter square Kelvin and the area as 1 meter square. So the things that are given is over. You have to find the total heat transfer Q, the first subdivision, and total heat transfer Q, the first subdivision, and the second subdivision, the outlet temperature of water, so which means T2, the exit temperature of the cold fluid, and the outlet temperature of oil, which is the exit temperature of the hot fluid, which is T2, and yeah, that's it. So these are all the things you have to find out. So now let's get into the solution. So we can find, you have to find capacity rate in NTU based solution. So we are going to solve this problem by total heat transfer Q, the first subdivision, and the second subdivision, the outlet temperature of water, so which means T2, the exit temperature of the cold fluid, and the outlet temperature of oil, which is the exit temperature of the hot fluid, which is T2, and yeah, that's it. So these are all the things you have to find out. So now let's get into the solution. So now let's start solving this problem. As I told you, we have to solve this problem using NTU method because we have two unknown temperatures to be found out. So in this case, NTU method could be very handy. You should never use LMTD method for this, so please make note of it. So the first step in this is to find out the capacity rate of hot fluid, which is oil. It is m dot h cph. So now the mass flow rate of the hot fluid oil is given as 0.144 multiplied by 2100. So we get capacity rate as 302.4 watt per Kelvin. And again, the capacity rate of cold fluid, which is water, so it will be m dot c cpc. So m dot c, the mass flow rate of water is 0.333 given in the problem, multiplied by its specific heat capacity, which is a standard value. So now we get 1381 watt per Kelvin using your calculator. So now, out of these two C's you found out, you have to find which is the least value. In these two, C min is how you're going to call it, 302.4. So C max will be 1381.3. So we will name the least value as C min and the large value as the 1381.3. Alright, so now the next step is to find C min by C max, which will be 302.4 divided by 1381.3. This will give you a value of 0.218. So the next step is to find C min by C max, which will be 302.4 divided by 1381.3. This will give you a value of 0.218. So C min by C max is 0.218. So now we have the relation NTU is equal to UA by C min. So this relation is used to find out the NTU, the number of transfer units for this problem. This relation is available from your HMT data book, page number 151. Alright, so now NTU will be, U is given as 1000, area is 1 meter square, Cmin is 302.4. So NTU will be 3.3. So this will be the value of NTU. Okay. So once you found out the NTU value, the next step is to find out the effectiveness of the heat exchanger epsilon. So you have to refer HMT data book, page number 163. You will see a graph. Okay, you will have a graph like this. So this will be the x-axis, this will be the y-axis. So in the x-axis you will be having NTU, and in y-axis you will be having the effectiveness epsilon. Alright, so now you have the NTU value now, which is 3.3. So just draw a straight line, 3.3. You might be having so many curves here running in this graph. So what you have to do is, so you have to draw a vertical line from the NTU value you have just found out. You just draw a vertical line and touch the Cmin by Cmax values here. So all the curves here represent Cmin by Cmax values. Our value is 0.218. So touch the curve which has the closest Cmin by Cmax value, which is 0.218. So once you touch that curve, you draw a horizontal line touching the y-axis. The corresponding value here will give you the effectiveness, which will be 95% from your graph. So the x-axis represents NTU, which is 3.3, and the y-axis represents the effectiveness, which is 95%, or you can write it as 0.95 also. So the maximum heat transfer possible will be Cmin into T1 minus T1. So this relation is also available in your data book. So please note it down and substitute Cmin value. T1 will be 95 and T1 will small case T1 will be 20. So Qmax will be 22680 watts. So this is the maximum possible heat transfer which is asked in the problem as the first subdivision. So now we will find the heat transfer. So you should know that the effectiveness of the heat exchanger is nothing but Q by Qmax. So you have the effectiveness value, which is 0.95, and the total heat transfer by the maximum possible heat transfer, which is 22680. This gives you the total heat transfer value as 21,546 watts. So this will be the total heat transfer. So this is your maximum possible heat transfer in that exchanger. Okay. So now total heat transfer is given as MC CPC T2 minus T1. So this is your familiar equation which you already know. This is also equal to MH CPH T1 minus T2. So remember, this is always large temperature minus small temperature. Remember that. Okay. So now we have a large value minus smaller value. Okay. So now we have 21546 is equal to MC, which is mass flow rate of water, 0.33 into 4186 into T2 minus 20 degrees Celsius. So now you can easily find the temperature T2, which is the exit temperature of the cold fluid, which is 35.5 degrees Celsius, which is asked in the problem. Okay. So this will be the outlet temperature of water at um, T2. Okay, temperature of water at T2. Okay, and then now we have another relation which is m dot Cph T1 minus T2. So we know that Q1 is again 21546. M dot H will be 0.144 multiplied by Cph is 2100. T1 will be the one you have to find out, sorry, 95, and T2 will be the one you have to find out. So now T2 value will be 23.75 degrees Celsius. So this is going to be your outlet temperature of the oil. So that's all.